When you look at a massive transformer, its nameplate rating, like say 11 kilovolts to 415 volts, looks like absolute fact, right? But really, it's just a claim on a piece of paper. In this explainer, we're going to dive into exactly how we prove those numbers are real before that equipment ever sees a live grid.
Because before any transformer leaves the factory floor, it has to undergo a rigorous series of interrogations. We have to turn that static nameplate claim into verified, undeniable proof. Factory acceptance tests are really where the theoretical design meets cold, hard physical reality. It's essentially the ultimate lie detector test for a transformer, and it's absolutely crucial for ensuring safety and reliability out in the field.
So here is our lineup of the three core winding tests: transformation ratio, phase displacement, and winding resistance. This triad is completely non-negotiable. They are the gatekeepers. If a transformer passes 2 but fails even 1, it does not ship. Period. Each test looks at a completely different aspect of the winding's integrity, and together they build a complete picture of the internal electrical health.
Let's start with the first gatekeeper, the transformation ratio test, or TTR for short. What we do here is apply a known low voltage to one winding, say the high voltage side, and measure exactly what comes out the other side on the low voltage winding. It's a direct verification of the physics. If the ratio of what we put in to what we get out perfectly matches the nameplate turns ratio, well, then we know the winding count and the fundamental connections are spot on.
But here's the kicker: the tolerance. How close does it actually need to be? The answer is incredibly strict. We're talking plus or minus 0.5%. And that's not just at the nominal rating. This exact tolerance must be met at every single tap position. The tap changer adjusts the turns ratio in steps to compensate for incoming voltage variations. And the TTR test meticulously verifies every single one of those steps to ensure the entire range is within that razor-thin 0.5% margin. To put that into perspective, let's look at some real factory acceptance test data from a Schneider electric transformer. Take tap 1, for example. The theoretical calculated ratio is 26.094, and the actual factory floor measurement came in at 26.088. For tap 2, it's 25.472 theoretical versus 25.544 measured. Both are well within that 0.5% tolerance. The math perfectly matches the metal. Okay, so once the turns are verified, we move to the second test, phase displacement. This test confirms that the vector group is correctly implemented. Think of a common configuration like DIN 11. This dictates exactly how the three phases are wired together internally. Because it's not enough to just step the voltage down, those internal winding connections have to be pointing in the exact right electrical direction. This ensures that the phase shift between the primary and secondary sides is exactly what the system design expects, which is absolutely vital if you ever plan on paralleling this unit with another one. Time for a quick interactive check. Think about this. If the TTR is dead on within 0.5% and the phase displacement perfectly confirms our DIN 11 vector group, are the windings fully healthy? Is this transformer entirely good to go and ready for the grid? The answer is a stark no. Those first two tests are incredibly important, for sure, but they only verify the math and the electrical direction. They verify the turns count and the connection topology. What they absolutely do not tell us is the physical health and physical integrity of the copper inside that tank. As far as the physical build is concerned, we are still totally flying blind. Let's use a quick analogy to see how this all builds together. Think of a master tailor checking a bespoke suit before handing it over to a client. Checking the fabric length, that's like our transformation ratio. Do we have the right amount of material? Checking the pattern direction is our phase displacement. Is it sewn facing the right way? But neither of those checks tell you if the seams are actually going to hold when you move. To check the seam strength, you need a completely different test to look for a completely different failure mode. And that brings us to the missing piece of the puzzle, our seam strength test, winding resistance. This test uses a precision DC resistance bridge to measure the actual resistance of each phase. By pushing a direct current through the windings and measuring those tiny resistance values, we can reveal hidden physical dangers. We're talking loose bolted connections, poorly crimped joints, damaged copper strands, or even a tap changer contact problem. These are the physical defects that the TTR and phase tests are completely blind to. So to summarize this absolutely crucial concept, ratio and phase verify that the transformer was designed correctly and wired in the right configuration. But winding resistance, that checks the actual physical build quality of the unit standing right in front of you. It closes the gap between the theoretical design and the physical execution. Without it, a hidden loose connection could easily turn into a catastrophic hotspot failure once the unit is actually energized in service.
So we've covered how we prove the ratio and the phase, and exactly why resistance testing is the vital final piece of the puzzle. But what happens when that resistance test actually catches something? In part 2 of this explainer, we're going to look at a real-world scenario where this exact test caught a 4% deviation, exposing a dangerous bad crimp before it ever left the factory. It begs the question, if this single test hadn't caught it, what kind of ticking time bomb would have been shipped to the grid? We'll find out in part 2.